All right, so today's lecture is about predicting motion and using velocity formula to allow us to calculate different positions on a graph. There are a couple of terms that we need to understand. The first one is interpolation, and interpolation is using a data set to predict a value within its range. What I'm getting at here is that if this was our graph, we would be looking to maybe potentially identify what this point is on our line. That's interpolation. We can think of it as interior, and as a result of that, that will give us our value on the line. And then extrapolation would be trying to identify maybe a spot out here beyond the scope of the graph, or maybe over here beyond the scope of the graph. So we could think of that as exterior. Okay, so we're going to use the concepts of interpolation and extrapolation to go ahead and calculate values today. So the first thing that we need to talk about is using interpolation to go ahead and fill in a data table. So here's our graph, and we're going to use our graph to go ahead and fill in our data table. We know that at position 2, or at time 0, the position would be 2 meters, and we know that at time of 1, the position could potentially be 4 meters. And at position 2, if we follow this up, this matches with what we know is it's 6 meters. So we're going to write that as 6 meters. And then we know at position 3, because it's already filled in for us, but we're just kind of keeping track here, is 8 meters. And also at position 4 happens to be 8 meters as well. So we're going to write 8 meters, and position 5 appears to be 8 meters, and so on and so forth. And I think that I'd like you to pause the video for a second and go ahead and fill in the rest of this data table. Okay, and we're back. So if I were to go ahead and fill in the rest of these values, I would identify that at 7 meters, I am at 6.5, or 7 seconds, I'm at 6.5 meters. At 8 seconds, I'm at 7 meters. And wait, nope, I did that wrong. Oh, hold on, let's back up here a second. At 7 meters, or at 7 seconds, I'm at 7.5 meters, sorry. And at 8 seconds, I'm at 7 meters. And at 9 seconds, I'm at 6.5 meters. So that's going to help me. Now, if I go ahead and erase this stuff here, I can go ahead and now use my graph to answer the following questions. Predict the position of an object at 2.5 seconds. Well, I would go across and locate 2.5, and I would just go up and where it intersects and go over, and I would estimate, I didn't draw a really awesome line, but I would estimate that I'm probably somewhere around 7.5. Let's see, well, no, maybe just 7 seconds. So we'll just say it's 7 meters. Okay, and then if I was going to predict the position at 4.5 seconds, I would do the same thing. I would go, well, maybe find that point and drop down, and then go all the way across, and note that I'm at 8 meters. And if I predict the position at 6.5 seconds, let's see, 6.5 seconds would be something like this. And I know that it's above 7.5 because that's what the value was for 7. So I'm going to say that it's probably 7.75 meters. You could also write that as 7 3/4 meters, but that's kind of how we do interpolation. Extrapolation is a little bit more difficult, and I think that it's easier sometimes to go ahead and see what's going on if we go and we actually draw our lines. So I'm going to draw the line in here and just kind of fill some stuff in along the way, because that's going to help us. So I'm going to just try to trace this out here a little bit, like that. Okay, now, I still need to go back and fill in my data. And in the process of going back and filling in my data, I'm going to go ahead and just identify some values. So at a position of, let's see, at a time of 1 second, I was at 6 meters. We learned how to do this a little bit in the slide before. At a position of 2 seconds, we are at 4 meters. At a position of 3 seconds, we're at 2. At a position of 4, I would say at a time of 4, we are at a position of 2.5. Meters. At a position of 5, we were at 3 meters. At a position of 6, we are at 3.5 meters. At a position of 7, we are at 4 meters. At a position of 8, we are at 4.5 meters, and I think that we're good now. It's asking us to predict our value at 11 seconds. So what I'm going to do is I'm going to take a look and say, well, if my line extended, that tells me that at 10 seconds I would be at 5.5 probably, and at 11 seconds I'm going to continue my line, so I'm going to guess that that's probably going to be about 6 meters. Okay, then I'm going to go ahead and say, well, I'm going to notice some things about my graph. I notice that every 2 I go up 1. So that tells me that tells me something about the slope, but we'll talk about that a little bit more detail in a second. So in this particular case, we're trying to figure out what it would be at 15. So if at 9 it was 5, 11 we said was 6, 12, 13 would be another one, so that'd be 7, and then 14, and then 15 would be another jump of 1, so that's probably going to be 8 meters. And that's one way to do it, but it's not always the most efficient way. For example, I'm going to go back and fill these values in, which is 6 and 4 and 2.5 and 3 and 3.5 and 4 and 4.5. But if I was going to go by 2s and figure out what 75 was, that would be a lot of effort on my part. So what I'm going to do is I'm going to go ahead and do a couple of things. The first thing I'm going to do is I'm going to calculate the velocity of my line. So I'm really going to be only focusing on this portion of my line of my data, because 75 is so far out from there. So I'm trying to get to 75 seconds. So I'm going to first calculate my velocity, and I know that my formula for velocity is change in displacement over change in time, which is x2 minus x1 over t2 minus t1. And so I'm going to choose a couple of points to work off of. I'm going to choose 9 and 5, and I'm going to choose 3 and 2. And I'm going to choose those because those were values that I already had. Those are values that are already given to me, so I know that there's nothing wrong with them in terms of the data. So I'm going to say that for x2, which would be my value here, this is x2 and this is t2, and this would be x1 and t1. I'm going to go ahead and fill my values in. So my x2 is going to be 5 meters over 9 seconds, and my x1 is going to be 2 meters over 3 seconds. And so when I calculate that out, or simplify that rather, I'm going to get something like 3 meters over 6 seconds, which will become 0.5 meters per second. So the velocity of this particular line, or the slope, which means it's the velocity, is 0.5 meters per second. So now I'm going to use 0.5 meters per second to calculate the time, or the position at 75 seconds. So I'm going to take velocity is equal to change in x over change in time, and I'm going to remember that I just calculated my velocity to be 0.5 meters per second, and that's going to equal, so I'm trying to figure out the object at 75 seconds. So 75 seconds is going to be my T2. So I'm looking for 75 seconds, and my x2 is what I'm trying to calculate. So I'm going to leave that just like that. Now I'm going to pick another point on the line, and I'm going to go ahead and I'm going to pick this one again, in large part because it's the beginning of this portion of the line. So that's going to be my x1, which is 2 meters, and my t1, which is 3 seconds. So now I'm going to go ahead and simplify what I have. So I'm going to go and move this over here, and I'm going to say that 0.5 meters per second will equal x2 minus 2 meters over 75 minus 3, which would be 72 seconds. So now I'm going to do some algebra, and I'm going to move 72 seconds to the other side by multiplying. So I'm going to take the 0.5 meters per second equals x2 over 72 seconds, 72 seconds minus 2 meters, and I'm going to multiply both sides by 72. And when I do that, seconds cancels out. So 72 times 0.5 gives me 36. 36 meters equals x2 minus 2 meters. Well, now what I'm going to do is I'm going to just go ahead and I'm going to solve by adding 2 meters to both sides. And I'm going to come back up here because I'm kind of running out of room. I'm sorry if you are too. And so that's going to tell me that the value for x2 is 38 meters will equal x2. So at 75 seconds, the object will have traveled 38 meters. It's not too bad. It's a little work, not too bad. Now we need to go ahead and figure out what happens to an object's motion 3 seconds before the start of the graph. Well, I need to go back and fill these values in just so that we have them. So it's 6 and 4 and 2.5 and 3 and 3.5 and 4 and 4.5. You're all looking at this. We have this line here and we have this line here. But this time we don't have to calculate the velocity because the velocity hasn't changed. So I know that my velocity is equal to 0.5 meters per second. So what I'm going to do is I'm going to use the 0.5 meters per second and I'm going to figure out where the object is 3 seconds before the start of the graph. So we're going to actually be focusing on this part here, which actually tells me that I do need to go back and calculate the velocity because that's a different thing. So let's erase this and start over a little bit. So here we go. So I am going to calculate my velocity here. So velocity is equal to x2 minus x1 over t2 minus t1. So in this case, my x2 is going to be 3 seconds. What's going on here? Okay. So I'm going to be focusing on, let's see, where are we at? I'm going to be focusing on, let's see, 3 and 2. And I'm going to be focusing on 0 and 8, because those are points that I know. So 0 and 8 is my x1, t1, and 3 and 2 is my x2, t2. So when I go and fill these values in, I'm going to take my x2, which is 2 meters, over 3 seconds, and my x1, which is 8 meters, over 0 seconds. So when I subtract this out, I get when I simplify this, I get a value of, let's see, a negative 6 meters over 3 seconds, which is going to be a negative, let's see, 6 divided by 3 is 2. A negative 2, what did I draw here? That's crazy talk. That would be a negative 2 meters per second. Okay, so now I know my velocity. So my velocity is negative 2 meters per second, but I'm going to now need to figure out what's going on 3 seconds before the start of the graph. So we still have x2 minus x1 over t2 minus t1. But this time I'm going to be focusing on, I'm going to say that that this is going to be my x2 and my t2 this time, because that's kind of like my beginning part of my graph. So I'm going to say that at x2 is 8 meters and 0 seconds, and I'm trying to figure out where the object's location is prior to the start of the graph. So I'm looking for x1 and 3 seconds. So in this case, I'm going to have, when I simplify this, I'm going to have 8 meters over negative 3 seconds. Nope, I lied. 8 meters minus x1 over negative 3 seconds. And all of that equals the negative 2 meters per second. So I need to go back and simplify this and move that 3 to the other side. So I'm going to write 8 meters minus x1 equals negative 2 meters per second over negative 3 seconds. So I'm going to multiply both sides by negative 3 seconds. And that's going to get me 8 meters minus x1, which will get me, let's see, 2 times negative 3. Let's see, negative 2 times a negative 3 is a positive 6. And then because this is seconds, my seconds cancel out, and I'm going to be left with meters, positive 6 meters. So now I'm going to go ahead and I'm going to, let's see, ooh, geez, what's going on here? I'm going to subtract 8 to both sides. So that's going to give me a value going over here. Let's see, it's going to be a negative x1 equals, let's see, 6 minus 8 will be a negative 2. And then when I divide both sides by a negative 1, my x1 is going to be 2. So that tells me that 3 seconds before the graph started, my position of my object is going to be 2. Oh, that's kind of a lot. But it's not awful. It's just kind of keeping track. So now we need to talk about predicting motion and Forrest Gump and some other things. So again, we're going to determine our velocity, and we're going to use our velocity to calculate the missing information using the formula below, and then we're going to solve for the missing value. So here's our deal. So and I'm going to use the only part of my graph, and you guys have a much bigger graph or data table, but the only part of my data table that gave me two values. Page here says calculate Forrest's velocity. So this time, I'm going to calculate Forrest velocity by using change in x over change in t. And I'm just going to be simple about this. So I'm going to take my 480 miles over 80 hours. And I can be simple about this because the other option would be 0 and 0. So let's see, 480 divided by 80 will give me a value of his velocity is 6 miles per hour, okay? So his velocity is 6 miles per hour. And that's going to be important for the rest of this guy here. So we want to figure out how many hours he's been running when he reaches Selma, Alabama. So if we know that his velocity is 6 miles per hour, we're going to say that velocity is equal to x2 minus x1 over t2 minus t1, and we know that the velocity here is 6 miles per hour, and we know that x2 in this particular case is 80, so that's 80 miles, and we're trying to determine how many hours, so that's going to be t2, and I'm going to try to make this as simple as possible. So I'm going to go back to Greenbow, Alabama, and I'm going to say that his initial was 0 miles and his initial time was 0 hours, not seconds. So in this case, when I simplify this, I have 6 miles per hour equals 80 miles over T2. So 80. So I'm now going to multiply both sides by T2. And so that will give me, I'm going to simplify this, T2 times 6 miles per hour will equal 80 miles. And if I divide both sides by 6, T2 tells me that's 80 divided by 6 will be roughly 13.3 hours. So this guy has been running for 13.3 hours. Whew. All right, one more, and then we're done. And you guys can finish the rest and go from there. So using Forrest's velocity, calculate how many miles he has run when he reaches Jackson, Mississippi. So let's see. We know that his velocity is 6 miles per hour. And we know that he has a time of 44 hours. So let's see. So we're going to use velocity is x2 minus x1 over t2 minus t1. So we know that his velocity is 6 miles per hour. And we don't know what his distance is, but we do know that his time is 44 hours, okay? Now, I'm going to go back and I'm going to use, again, I'm going to go back and use total miles jogged because that would be easier. So 0 miles, so we're talking about Greenbow, and 0 hours. So when I go to simplify this, I'm going to have 6 miles per hour equals x2 over 44 hours. So what I'm going to do is I'm going to multiply both sides by 44. So 44 times 6 miles per hour equals x2 . So I'm left with 44 times 6 miles per hour equals x2. So 44 times 6 in this case will get rid of hours, and I will be left with, he's traveled, let's see, 264 miles when he gets to Jackson, Mississippi. And that's that. So your homework tonight is to do worksheet number 3, and worksheet number 3 has got problems similar to this. So thank you for listening, and good luck.